Our essential question in this video is how do I solve word problems? You'll see this essential question a number of places in your notes. We want to keep on taking the things that we're learning in these units and applying them to word-based problems. So here's our question. A baseball player throws a baseball. The height of the ball in feet can be modeled with the function f of x is equal to negative 16x squared plus 64x plus 5, where x is the time the ball is in the air in seconds. We've got time in seconds. X is representing time in seconds, and the function itself is the height of the ball in feet. So when you look at word problems regarding quadratics, you want to look at what are the two axes representing. In this case, we've got the x value, which is our input. That's going to be our x-axis. That's going to be the time the ball's in the air in seconds. And then f of x, which is the y value of our function, is going to be the height of the ball in feet. Okay, so let's solve this problem. We've got a quadratic equation in standard form. You've seen that before. Remember, when we graph a quadratic in standard form, we're going to find the vertex first, and we're going to put that in the middle or the third position of a table that you're going to sketch. Then you're going to go 2 points below that, 2 points above it, plug those x values into the equation, find the y value, and then plot and sketch the diagram. And when we do that, we're going to be able to figure out this question, which is, here's our final question: when will the ball hit the ground? If you look at the graph, the ball's going to hit the ground where y, or our height, is equal to 0. That's ground level. That's our x-axis. So class, if we find the x-intercepts, then we're going to be able to figure out where the ball is going to land on the ground. So let's go ahead and work through this equation. Step 1 of graphing a quadratic in standard form is, let's identify a, b, and c. So our a value here, we can see it's the coefficient on the squared variable. That's negative 16. Our b value is the coefficient on the non-squared variable. That's 64. And we have a c value here, which is equal to positive 5. To find our vertex, we're going to have to find the x value of the vertex first, and that is found with the formula negative b over 2a. b is 64, so the opposite sign of 64 is negative, so positive 64 changes to negative 64 because we're looking for negative b. And then we've got 2 times a, which is negative 16. If we work that out, you can put that in your calculator already, but I'm going to write it out for you. Negative 64 over negative 32. Let's go ahead and do that. So we're going to do parenthesis negative 64. I just want to make sure the calculator knows that the negative or the minus, the negative sign goes with the 64. You don't have to put the parentheses here. Divided by, and then in parentheses negative 32. And we've got a nice even positive 2. So that is equal to positive 2. That is the x value of our vertex. And now we're going to go 2 x values below that and 2 x values above that. Let's go ahead and solve for the vertex here. So let's plug in the number 2 into our equation. I'm going to show our equation there. And we're going to put in, we've got negative 16, and then in parentheses 2. We're going to square that, plus 64, parentheses 2. There's our x value again. And then plus 5. We press equal, and we get 69. So the value here in our table is 69. There's our vertex. And then if you were to, again, practice this class, plug in 0, 1, 3, and 4. When you do that, you're going to get 5 when you plug in 0, 53 for 1, 53 for 3, and 5 for 4. Let's go ahead and plot those. Okay, we got a problem because we can't fit those on our graph. Let's go ahead and do some labeling of our graph. The first thing you want to make sure you know, class, this is a real word problem. That means you got to tell our listeners or our teacher or whoever is looking at our work, what does our graph look like? And what are our axes actually representing? Well, the x-axis is going to be time, and that's in seconds. SEC is good for seconds. And then this, the x or the y-axis, I'll try to do this if I can, angled here. This is going to be height. I can't turn my paper sideways like you can, so I'll do my best. That's height, and that's going to be in feet. And now if this is 0, we're going to have to get to 69. So let's go by 10. So 10, 20, 30, 40, 50, 69 to 70. That means we can put 70 right here. And let's just write a few numbers. I'll put 10 there. Let's put 30 there. We'll put 50 there. So we're going to go by tens. And then our seconds, the most seconds we have is 4 on our graph. So we can go, looks like we can go every other one. So 2 units, that's 1. And then 2 more units is 2. And there's 3. And there's, and there's 4. So when you're doing a graph, try to use as much of the graph as you can. It'll make your, if you have to estimate values, it'll make your estimates much better. Alright, so here we go. We've got time and height. Let's plot our points. We've got 0 and 5. That's about right here. 1 and 53. That's 60. So 53 is somewhere around here, let's say. 2 and 69, that's right below 70. And then that's the vertex, class. That means we know this other point is going to be reflected across the axis of symmetry. It's going to go right here. Same horizontal height. And then we get to 4, and we're back to 5 right here. And then again, you can do a lot better job than I can. I would now sketch my parabola. Let's try to do that. I'm going to use dashed lines, do the best I can. Remember, parabolas are never pointy, so try to make it a curved shape. We're going to come down right here. Let's fix that last one. And you're going to see that as we go down through this point, we're going to cross the x-axis right about there. And if we kept going through this point, we would cross the x-axis right about there. Not quite there. Actually, we'd move it over and be a little closer. Actually, that dot is pretty good. Okay, so there is our parabola. The time that the baseball is in the air, and the height, how high is it at different time values. So the question is, when will the ball hit the ground? Well, think about this. We don't know exactly, but we can have an approximation. You can see the ball hits the ground right about here, which is about, if the question is when, we're asking about time. I'm going to circle this. You guys can see this when. That's time. What time will it hit the ground? Well, it's going to hit the ground about 4. If this is 4, this is 4.5. I would say it's probably about 4.1, maybe about 4.1. And it actually technically looks like it hits the ground over here at negative something also. Maybe it's negative 0.1. So let's take a look. Here's our x-intercepts. I'm going to mark those on the graph, right? About right here and about right here. So we can use the graph to estimate. So I'm going to make a note in our word problem. Remember, word problems require word answers. The estimated x-intercepts. Our last question, I think we had exact x-intercepts because when we plugged them in the table, we got the x-intercepts. But this time we don't get the x-intercepts. We're going to have to estimate. So the estimated x-intercepts are at about negative 0.1 and about 4.1. Now you could have guessed 4.2, 4.3, somewhere around there. Okay, now let's put another explanation here. Since time cannot be negative. Why am I writing that? Because class, take a look. We have two values that x can be. Two values when the ball is on the ground. But the negative 0.1 means nothing. That's prior to us throwing it. So that's not even a logical answer. So when you get a negative time, you just ignore it. So since time cannot be negative, then our final answer is the ball. That's not a very good the. Make that a little better for you guys. The ball will hit the ground in approximately, and I just abbreviate APPROX for approximately 4.1 seconds. You could have answered this based on the graph. The ball will hit the ground in approximately 4.1 seconds. I like that you can explain to me that there's two x-intercepts, but the negative one doesn't make any sense in this particular question. All right, let's go to the next one. Here's our second word problem, and let's go ahead and read this. Michael drops a ball from a window on the second floor of his house 10 meters above the ground. Alright, so we know what our starting height is. The height of the ball in meters is modeled with the function h of t is equal to negative 4.9 t squared plus 30. And this is actually a typo, class. And I think your flip book is probably corrected, but in case it's not, this is supposed to be 10. Negative 4.9 t squared plus 10, where t is the time the ball is in the air in seconds. Now here, so far this lays out kind of like a regular quadratic graphing problem, but here's where the difference is. Anna is below the window and catches the ball 2 meters above the ground. How long will it take for the ball to reach Anna's hands? So in this case, unlike the previous example, the ball is not going to hit the ground at height 0. We want to know how long it takes for the ball to drop down to Anna's hands, which are actually 2 meters above the ground. We're going to set this up pretty much the same as we usually do, but then let's see how the answer might be a little bit different. So the first thing we're going to do is we're going to go ahead and see that we have to find the vertex of this quadratic equation. So let's go ahead and write a few things we know. We know that A is equal to negative 4.9. Our B value, there is no B value in this quadratic, so B is equal to 0. And then our C value is equal to 10. So there's our A, B, and C value. Now we can go ahead and plug those in, or the A and the B value, into our formula for the x value of the vertex. So we know that that formula is negative b over 2a. Our b value is 0, so we can write 0, or if you want to write negative 0, that's fine. Negative 0 times over 2 times negative 4.9. Well, we already know that if there's a 0 on the top of our fraction, the whole thing changes to 0. 0 divided by anything is equal to 0. So we know that the x value of our vertex is 0. So now we're going to go ahead and graph two numbers below that and two numbers above that. Oops, not a 1. Two numbers above that. All right, let's go ahead and do that. Let's plug in 0 into our equation, and I'm going to go ahead and do that real quick. We'll do one of those, and you can do the other ones on your own if you want to. I'm going to put in, my equation is negative 4.9. Oops, I'm supposed to put that in parentheses. So parentheses, negative 4.9, parentheses, oh, I'm sorry, I'm not supposed to do that either. Negative 4.9, the parentheses is for the t value. So parentheses, let's do the negative 2 first. And that's going to be squared plus 10. And our first answer is negative 9.6. Alright, let's do one more together. So let's do the negative 1. So we're going to put negative 4.9 and in parentheses negative 1 squared plus 10. And we've got 5.1. If you check the other numbers, you'll find that at 0 you'll be at 10, at 1 you'll be at 5.1, and at 2 you'll be at negative 9.6. Alright, so let's go ahead and graph these. And remember, let's go ahead and label our graph, since we always should do that. The x-axis is going to be time. I'll just put S for seconds, and the y-axis is going to be height, and that's in meters. I'll put M for meters. Alright, let's go ahead and scale. So looks like our highest point is 10. That's where we started. So let's see, if I go 1, 2, 3, 4, 5, 6, 7, 8, that's not going to get me where I need to go. So I'm going to have to, I guess, go by 2's. So 2, and then that's 4, 6, 8, and 10. So there is 10 meters above the ground. And then our time looks like we go out to 2 seconds. Look at the table, class. You see that the height now is at negatives at 10. That means we know it's going to hit the ground before it goes 2 seconds. So let's make sure that we at least graph 2 seconds. I'm going to go 1, 2, 3, 4. Let's just do 4. And there's 1 second. And 1, 2, 3, 4. And there's 2 seconds. And then we know, class, that if you think about this, if I divide up the seconds by 4s, that's 1/4 or 0.25, 0.5, 0.751, 1.25, and so on. So now we've got our axes labeled and scaled. Let's go ahead and plot some points. We've got at negative 2, negative 1. Let's do 0 first. At 0, we're at 10. That's actually our vertex because we're just dropping the ball from the second floor. We're not throwing it, we're just dropping it. So that's probably going to be our vertex. Actually, it is our vertex, sorry, because we already have the vertex right here. We know this is our vertex. At 1, we're at 5.1. This is 2, 4, 5 is about right in the middle there somewhere. And now at 2 seconds, we're at negative 9.6. The problem is that we're actually going so far off the graph that I can't plot it. So here's probably a good idea, class, is just to make sure your graph is fairly accurate, let's go ahead and plug in 1.5 as well and see what we get. So we know it's going to maybe just be below the ground or just above the ground. Let's try 1.5 so we can get another point on our graph. So we'll go ahead and do this. This is negative 4.9 times 1.5 squared plus 10. And we end up getting negative 1.0. Oh, that's perfect. So we're at negative 1.0. So that means at 2 seconds, we're going to be at negative 1. That's going to be about right here. Oh, sorry, not at 2 seconds. At 1.5 seconds, we are right here. There we go. That makes more sense. And if you want to label your negative values on your x-axis, you can do that. That was negative 2, and that makes this negative 4. And this would be negative 6. Now we have a little bit more information to actually draw a more accurate graph. So I'm going to try my best just go ahead and use some dashed lines here to go through my points. You go ahead and sketch your parabola as accurate as you can. That looks like a pretty good parabola. So now we've got our graph done, but here's where our issue is. We're not being asked when does the ball reach the ground, because if we were, you would look at your graph right here and say, well, this is 1.5. It reaches the ground just before 1.5 seconds. You can see how close we are. We're just below 0 at 1.5. But that's not where we want to be. We want to be at, take a look at where Anna catches the ball. She catches the ball 2 meters above the ground. That puts us right here at 2 meters. I'm going to put a line right here so you can see. Right at this point is where our parabola is at 2 meters above the ground. So let's take a look at that. It looks to me like we're at 1 second. There's 1.25 and this is 1.5. I'm going to call that somewhere around 1.3. Somewhere around 1.3. So let's just draw a little note here. This looks like it's approximately 1.3 seconds. Alright, now just to show you this, you can actually test your estimate to see how close it is. Let's go ahead and take our equation and teach you guys how to do this. You can take our equation now and let's plug in 1.3. If we end up with a value that's close to 2, that means that's an accurate estimate of how long it takes the ball to be 2 meters above the ground, which is where Anna is catching it. So let's go ahead and try that. I'm going to go ahead and put in here, let's see, did we call this function f? No, function h. So I want to know, what is h at 1.3 seconds? Let's go ahead and plug that in. Negative 4.9 times 1.3 squared plus 10. And let's see what we get. So calculator, negative 4.9 times 1.3 squared plus 10. How close are we? We're at 1.719. So I'm going to write that 1.719. That's a little bit low. We've actually gone a little bit too far. At 1.3 seconds, the ball has actually fallen farther. It's less than 2 feet above the ground, so we're a little bit too far. So if you want to get more accurate, let's try this. Let's try h of 1 point. Instead of 0.3, let's go ahead and use 1.25. Let's see how close we get there. So I'm going to put in negative 4.9 times 1.25 squared plus 10. Let's see if we get closer to 2 meters above the ground. I might have said feet before, so 2 meters above the ground. Alright, let's plug it in. So again, we've got negative 4.9 times 1.25 squared plus 10, 2.34. So at this value, we're at 2.34. So now we haven't quite fallen long enough. And so based on this, 1.3 and 1.25, we can pick a number exactly in between those two. And the way you do that is you just take the average of those two. So I'm going to take 1.25, I'm going to add 1.3, and I'm going to divide that by 2. That will give me the average. If you put the top part in parentheses, you can do this all at one time in your calculator. 1.25 plus 1.3, and now we're going to parentheses and divide that by 2. There's our average, 1.275. So probably a more accurate estimate of how long it takes to drop from 10 meters above the ground to 2 meters above the ground is 1.275. And so I can write my final answer here is it takes approximately 1.275 seconds to reach Anna's hands. You could say to reach Anna's hands, you could say to be 2 meters above the ground, but I'm gonna say reach Anna's hands because that's what the question says. Reach Anna's hands. To reach Anna's hands. So you see this is a little bit unique in that we're not actually wanting the ball to reach the ground. We draw our parabola like we normally would, but then we look at, okay, where is the point that is actually 2 meters above the ground, and that will tell us approximately how much time has gone by. And alright, so there gives you an example of how to deal with a little bit more difficult problem than the previous problem.